Welcome to Day 20 of Advent of Code 2023. Today we will be dealing with pulse propagation. Let's begin. The elves need to activate the machines on Gear Island by sending pulses through communication modules. Different module types handle pulses in their own unique ways. Pulses that are sent through the system are either high or low, and modules process pulses in the order that they are sent. After pressing a button, the broadcaster will send all its pulses, and we cannot press the button again until subsequent pulses are handled. So, given the configuration of the modules as our input, and after pressing the button 1,000 times, then what is the total number of low pulses and high pulses that have been sent through the system? And finally, for part 1, what is the number when you multiply the low and high pulse counts together? To further clarify, the following module types can be encountered in our input. First, we have the flip-flop modules, which are prefixed with a % sign. They toggle between on and off states based on received pulses. Then, secondly, we have the conjunction modules, which are prefixed with the ampersand sign. They remember the pulse types from inputs and send a low pulse if all of the inputs last pulsed high. The system also has a single broadcaster module, which sends pulses to all destination modules as indicated in the input. Lastly, there is always a button module. This module is not explicit in the input, but when we press the button, we will cause the broadcaster to emit a single low pulse. Now let's have a look at some examples to strengthen our understanding of the problem. In this first example, we have a broadcaster, 3 flip-flops, and a single conjunction. Because the conjunction only has one input, it effectively operates as an inverter. Then once we press the button, we first send a low signal to the broadcaster. The broadcaster emits the signal to its children again. Then the first module that we should process next is flip-flop A. It received a low pulse, which is a reason for the flip-flop to switch state. Subsequently, it sends a high signal to flip-flop B. Now, you might think that flip-flop B thus needs to be processed with an incoming high pulse, but the signal that came before was a low pulse from the broadcaster, so we handle that next. As a result, B emits a high signal to C, and for the same reasoning, C emits a high signal to the inverter. Because the inverter now has a high signal on all of its inputs, it will send a low signal eventually. After all signals have been processed, you'll find that this particular system gets reset back to its initial state after every button press. This second example works slightly differently. It has 2 conjunctions and even one output module that itself is not an input for any other modules. After pressing the button, we'll get the sequence of pulses that you can see on the right. Please pause the video if you want to take a closer look. Now let's move on to the solution of part 1. It seems like this first part is just asking us to write code to simulate the system and count the pulses as a way to prepare us for part 2. So let's do just that. Because we're dealing with modules or nodes in a graph, which can have some state and a type, I propose to make a few dictionaries to keep track of state, type, children, and parents of every node. Then we just parse our inputs to populate most of the data, and we'll call connect parents to make sure our graph is connected bidirectionally. Then to solve the problem, we'll have 2 trackers for high and low pulses, and we will push the button 1,000 times. At the end, we should be able to just multiply the pulse counts together, and we'll have our solution. To make our code a little bit simpler to read and write, I propose adding 2 small utilities. First off is to alias a Boolean into low and high variables. Secondly, an enum can help us identify the type of each module. The key element of our solution then is to simulate one button press. Here we will have a queue with signals that still need to be processed in order, and we'll keep track of low and high pulses. Then while the queue is not empty, we extract the node name and the pulse signal from the front of the queue. The node type can then be inferred from the type dictionary. Next, we need to track if the current pulse is low or high, and finally we check per node type where the signal propagates to. At the end, we return the low and high signal counts. Propagating the signal, of course, works based on the node type. At the top, we have the broadcast module. We know that this has to be coming from the button, so we set the state of the broadcast module to low, and we return a list with all child nodes, and we indicate that they receive a low pulse. The flip-flop function we only enter if we receive a low pulse. The result is that we flip the state of the module itself, and we send its new state as the outgoing pulse to all of its child modules. Lastly, the conjunction module. Here we check if all parent nodes are currently emitting a high signal to the module. If all states are high, then the module emits a low signal. Otherwise, it emits a high signal to all of its children. And that's it already for the logic of the simulation. All that's left is parsing the input data, so for completeness' sake, here it is. I don't think the string parsing is that important here, but please make sure that you understand how the dictionaries with states and children are filled based on the input, as this is our graph representation. For part 2, we need to dive deeper. The final machine responsible for moving the sand down to Island has a module attached named RX. The machine turns on when a single low pulse is sent to that module. So the question for part 2 becomes as follows. Given our input, what is the fewest number of button presses required to deliver a single low pulse to the module named RX? The problem doesn't drastically change, but for the example, consider the following. Can we simulate the machine until the requested module receives the low pulse? What we're given at this point can be seen as a black box. We know that there is a broadcaster, and eventually, at some point, a signal should end up at module RX. You can give it a shot to just simulate, but you'll find that it shall take a long time before you get the answer that way. Can we do something smarter? The solution lies in analyzing the structure and behavior of the network. You'll find a structure that is roughly equivalent to the following diagram. On the right, you'll have your module RX, and its parent modules are 3 layers of conjunctions. The leftmost column of conjunctors activates cyclically based on flip-flops, of which we don't care too much for their underlying structure. The idea here, then, is that if you know the interval at which each conjunction activates, then you can determine when they all activate at the same time. So we find the cycle lengths of the conjunctions 3 levels deep, and we compute the least common multiple of the lengths. The solution outline then changes slightly. First off, we of course need to keep track of cycle lengths, so we'll create another dictionary for this. Then, let's track the number of presses, and we'll determine which nodes are the key nodes from which we can extrapolate our answer. Then while there are key conjunctions missing, meaning that we don't know the cycle length of all of them yet, then we'll push the button one more time. At the end, we'll be able to grab all the cycle lengths and just compute the least common multiple trivially using the Python math module. Finding those key nodes can be done recursively. Given the structure, we know that they are at some target depth. So while we're not at that depth, we recurse deeper. If we are at the correct depth, then we'll return a list of all conjunction nodes. Determining for how long we need to loop is as simple as seeing if any of the important conjunction nodes still has a cycle length of 0. Lastly, we need to make a small update to our conjunct function. Since we only emit a low signal once all our parents are high, we'll keep track of the number of presses in the cycles dictionary every time this occurs. In practice, this shall only occur once for every one of our key nodes. And that was it again. 2 more stars in the bag. In the meanwhile, we've passed into the new year, and I want to thank you all for your support and letting the channel grow to 300 subscribers in such a short period of time. Your support is truly amazing. Best wishes for the new year, and I hope you look forward to the next video.